Well, good morning, everybody, and welcome to the inaugural Robotics Summit and Showcase event. I'm all very glad that you are here to join us for this. We're very excited about what we've launched right here. If you look at the subtitle of what this event is about, it's really the international technical design and development event for building robotics and intelligent systems. But actually, there's one word that we omitted in there, and that's the word commercial. This event's focused on the development of commercial class systems as opposed to, say, hobbyist systems or even some research systems. So people who are looking to get into robotics as a business, an ongoing business to make money to do that so that they can keep this business going on. So the genesis, just very quickly before I introduce the first keynote speaker here, speak a little bit about the genesis of this event. Now, when we partnered up with Mass Robotics on this event to talk about what we should be doing here, we had a couple things in mind. One, we wanted to serve the greater robotics community and also the Boston robotics community. We wanted to drive that community, and at the same time, we wanted something that would have wide applicability and impact. And when you start thinking about that in terms of an event, you have a lot of ways that you can go. And I've been involved with robotics events before, and I know what works and what doesn't work, and where the openings are in this particular market, and how that market needs to be served, and what value you can bring. If you look at this marketplace, whether you're in the agricultural space or logistics space, the mil-aero space, the consumer space, the one thing you have in common are these robotic systems that think, act, and sense in the physical world. The one thing they have in common, regardless of whether you're in the consumer space or the military space, is somebody has to build those systems. And designing and developing commercial class robotic systems is very hard. You're talking about the combination of electrical engineering and mechanical engineering and systems engineering and certainly computer science. And it's a gating factor to the growth of this particular industry, the robotics and intelligent systems industry. So if you can create an event that adds value for the people that are doing that, building these commercial systems, there's an opportunity there. There's an opportunity for everybody in this audience, and there's an opportunity for WTWH Media and Mass Robotics, the people who are putting on this particular event. So we're very, very excited about it. So not only are we on the right track, because before you can invest, a company gets invested in or purchased or acquired, or they form a partnership or they deliver products, they actually have to build robust systems at a price that people are willing to pay. And that's what this event's all about. It's also an event for this community, and the fact that you're here at this particular event lends credence to the fact that the original vision for the Robotics Summit was correct, to emphasize and to focus on these particular issues. So thank you very much. You're as much a part of this event as anybody else here in terms of the sponsors and the speakers and everybody else. So again, thank you for being here. Speaking of the sponsors, I'd like to thank those sponsors. We have our platinum sponsor, Harmonic Drive, which has done a lot of work to get this thing off the ground. Our diamond sponsor, Sertronics, as well. And certainly all other sponsors and media, the analyst community, the associations, and everybody else. So it took a lot of people to kind of pull this together. Special thanks goes out to Tom Ryden and Joyce Solidopoulos at Mass Robotics. I mean, there are people that assist you with events, and then there are people who really assist you with events, and they're in the latter group there. I'd also like to thank the WTWH Media team. You'll see the folks with these little badges, so that would be Scott McCafferty, the CEO of WTWH, Steve Crow, as well, has been assisting from the Robot Report and also is a co-chairman of this particular event. Then Jen Kolatsky is also in terms of the ops and the ops team that she has brought together. They've done a fabulous job. I really have to thank them. One of the things I'd like to go through really quickly is the keynotes here. We have 4 keynotes, and they map to the development and design of these systems, the tools and technologies and platforms, so sensing, thinking and actuation, so cognition and actuation in the physical world. A track on design and development, so once you have the tools in place to sense, think, and act, how can you put them together with simulation tools or CAD tools or other types of products, robot operating systems, other types of testing tools. And manufacturability and production and distribution is also important, because once these things are done, how do you take them to the next stage? And then we also have a couple of sessions in the investment track, saying once you have those products completed, what's next for you? I have a couple of housekeeping announcements that I need to make. There's something called the Robotics Summit Passport Program. You should have received a piece of paper with a number of different companies marked on it. If you go through and visit all the exhibitors, there will be a drawing at the conclusion of the event for a Roomba and also an iPad. We have an app for the event, so you should have also received when you registered or picked up your badge the agenda, and you can see that there's a mention of the Robotics Summit app and how you can download it, as well as the Wi-Fi login. So all of that is here on this particular document. As far as today's events go, we have a series of 3 keynotes that are running initially. So we have the initial one will be Damion Shelton from Agility Robotics on bipedal locomotion and autonomous mobility. John Delchinos from Jabil, the 3rd largest contract manufacturer in the world, speaking about producing commercial class robotic systems. And then Adrian Kumar from DHL on designing a mobile service robotic system. After that, at 12:30, from 12:30 to 2, the Robotics Summit showcase is open. That's in the Marina Ballroom, so what you have to do is go upstairs, across the lobby level, up to the mezzanine level, and then you'll see signage for that to get you to there, and that begins at 12:30. It's just about a 2-minute walk. And then following after that's over a number of general sessions in the Lewis Ballroom, the Lewis Room, the Burroughs Room, and then the Harbor Ballroom as well. I would ask you if you could also turn off your cell phones. That would be very much appreciated at this time so we don't interrupt the speakers and give them a nice, a clear path in terms of getting their message across and bringing value to all of you. So with that, I know is rather quick. I'd like to introduce the first keynote speaker at this time. We're extremely happy to have with us here the CEO of Agility Robotics. They are the maker of the Cassie bipedal robot that you might have seen videos of, or maybe you've seen actually live demonstrations of. It's a fascinating piece of technology. Damien's here to talk about bipedal locomotion and autonomous mobility. Before Damion was the CEO of Agility Robots, he worked at 3 Rivers 3D, where he was CTO, and they developed different classes of laser scanners and other types of technologies. So without further ado, I'd like to welcome our first keynote speaker, Damion Shelton, and again, once more, thank you all for being here. Thank you.
So, the title of the talk is Bipedal Locomotion and Autonomous Mobility, and I'll explain why they may or may not be the same thing. If you think about autonomous mobility, it's typically in robotics been construed as a bit of an AI and sensing problem grafted onto a physics problem. And by that I mean, if you take a traditional approach to robotic design, you typically will start with the systems engineering, and then from a control theory standpoint, that's the plant, and you design a control system to go through and actuate the robot. Because of the complexity of the environment, if you're doing inverse kinematic style design, you have to have very complete world knowledge in order to do successful controls on the machine. If you think about this system, though, this gentleman has wisely decided it would be good to blindfold himself before slacklining across this canyon, and has taken the interesting step of removing sensing from the equation other than proprioception. So clearly, you can do very complex locomotion tasks like this without having a perfect map of the world, because you can blindfold yourself and intentionally delete the information. So that kind of asks the question, are high-level cognition and mobility separate problems? And as any good talk has, there's no actual answer here, but I want to talk through some of the issues. You can imagine on the left-hand case that there is a robotic design approach that's a bit like this problem, where you have a really good mobility platform and you graft a really smart AI on top of it. And to some extent, they're separable. So the horse can operate by itself, but without an understanding of high-level intent. Certainly the AI in this case can think things by itself without having the mobility platform to execute them. On the other hand, if you have a world-class athlete like Edwin Moses, who won a number of track and field meets back in the early 80s, back to back to back, that's not really a separate problem. So you can't imagine a case where an Olympic-class hurdler is really able to remove the cognition and planning from the mobility of the manipulation side. And there obviously is a spectrum here. So you can have machines that are more on the pick-and-place end that have very little in the way of active AI, or systems that are purely AI-based. Our interest in this, and this is Pittsburgh. Pittsburgh has some of the same problems that Boston does, but with hills. So if you have aging infrastructure, or the very cleverly designed ADA-compliant front stoop here for, this was actually co-founder Jonathan Hurst's house in Pittsburgh. If you imagine trying to have a robot that can move through the human world unfortunately contains things like this. It's hard to actually to argue actually this was even really designed for people, much less for machines. But there's lots of things out there like here. So on one end of the spectrum is a hyper-engineered environment. So imagine an Amazon warehouse, for instance, where you know down to the centimeter the placement of everything in the entire structure. Automating that environment with a robot is relatively straightforward, at least insofar as knowledge of the environment is concerned. With outdoor unstructured human environments, not only do you not have a reference map of the world, but the environment itself may be trying to actively kill you, like the sidewalk on the left side here. And unfortunately, that stuff will change. So we had a winter in Pittsburgh very much like you had here in Boston. A lot of freeze-thaw cycles, ground heave all over the place. The self-driving cars are breaking axles on potholes, which is a weirdly Pittsburgh thing to say because of our population of self-driving cars. But the point with this is that if you're trying to automate this environment, you can't rely on anything other than the fact that people, for better or for worse, can move through it. In terms of assessing mobility options, we've been very careful over the last 3 years as the company has existed to not misrepresent what we're trying to do. So we're not making the claim that legs are the right solution for everything. And in particular, there are some really good reasons why you might want to choose something other than legs. If you have a long distance to go on flat ground with a very heavy load, there's no reason to use anything other than a wheeled vehicle. It's the right choice. If you're trying to carry very heavy loads through broken terrain, tracked vehicles have been around for more than 100 years at this point. And if you're going through mud, carrying supplies out to troops in the field, obviously tracked vehicles are the appropriate choice. And then finally, for distances where you have to carry relatively light loads, medium to long distance, high speed, think things like organ donations between hospitals, that kind of application. Wings are clearly the right choice. All of these have their problems, though. So with wheels, stairs and obstacles are challenging. Tracks have a very military aesthetic in addition to some mobility issues. And then for wings, in Southern California, it might be possible to use those most of the year, but certainly not anywhere in the Northeast if you're taking into consideration weather. In terms of legs, legs in general are very good for human environments. As a consequence of us having legs as much as anything else, I'm sure if we had evolved with wheels, our environments would be good for wheels too. So people have asked us, well, why bipeds? And the answer is, well, there's obviously a spectrum here too of the number of legs that you can have. So Rex, which is a fairly well-known early legged machine, had 6 legs, had the nice feature of being statically stable. All things being equal, and they're obviously not here because the shaft robot at the bottom and Rex have very different styles of legs, but all things being equal, if you have legs of sort of equivalent complexity, more limbs means more actuators, which means more cost. 2 legs in particular are good for human scale tasks in human environments. And that's as much a form factor thing as it is anything else. I have a dog. Robots like Spot Many have amazing mobility, just like dogs have amazing mobility. There are probably lots of applications where that's a reasonable choice. Where it starts to fall apart a little bit is in a paradigm where you're interacting with people. So if you imagine a package delivery task at a business where the expectation is the package ends up on the counter, you end up having to add additional manipulators onto the back of it, so the arm that Spot Mini has on it, for instance, in order to reach the counter, whereas with a biped form factor, you end up with the manipulators at approximately hip height for a human. Now, the problem here is this is hard. So bipeds have been sort of what people have imagined the quintessential mobile robots being going back to the 1950s with the Westinghouse robots. But there are some significant challenges here. This was actually the first robot that Jonathan ever built on the left. This was an unnamed CMU biped from the 90s, back when he was an undergrad. And this has been sort of a traditionalist approach to making humanoids that actually is continued in commercial products today. So I'm not trying to point fingers and say, look, this is a terrible way of doing it. The idea that you would directly actuate each joint in the robot is kind of an intuitively relevant approach. So the idea here is if you look at people, you can identify all the degrees of freedom on someone's arm, all on the leg, put motors in each spot, and then control it. If you had a magic actuator, that would work fine. The problem when you start to address the physics of this is that as you place mass distally, either on your arms or your legs, you end up with these big pieces of inertia that are out there waving around along with the limbs. And if you're trying to do low-cost educational robotics that's not particularly dynamic and is instead trying to give you active control over all of the degrees of freedom of the robot, from a control standpoint, fully actuated as opposed to under-actuated or over-actuated, then that's an appropriate choice. The problem is, as you start to get up into dynamics, it would be a lot like having the car engine out there spinning around with the wheel of your car. It's a huge waste of inertia. You have to accelerate it and decelerate it as you do the movement. So there was some work that was done with someone who ended up actually being a collaborator of Jonathan's at one point. So this was Hartmut Geyer's work at CMU. Looking at, as I'm sure needs no introduction, Mark Rabert's spring mass work, from the 80s and continuing through to today. The work that Hartmut did was interesting because it was one of the first attempts to show that the spring mass model, the slip model, for those of you who are familiar with it, was sufficient actually to explain both walking and running. So running actually has been sort of a known problem for the slip model for a number of years. So the idea there is that you have an aerial phase in the gait, and it was known that you could do that with the slip model. And Hartmut's work was to show that you could actually use this very simple model to also explain walking gaits, which are more useful than running gaits in a lot of applications. So why does this matter? Well, this is an abstract mathematical model. It happens to map to observed physics for animals, in this case, humans walking across force plates. But there's lots of cases where starting with a bunch of math and ending up with a physical product leads you in a very different direction. So our explanation with this is if you look at the history of flight, people were inspired by birds, in some cases tried to have early machines that would flap their wings, and ended up with, a modern 787 is derived from that pool of math, but looks nothing like a bird. So there's no particular explanation or expectation, that you would start with this math and then end up with something that happens to mechanically look like a machine. But that is in fact what we find out. So from a mechanism standpoint, why does this matter if you're trying to build products? So if you have this relatively straightforward model on the left, so this is the spring-loaded inverted pendulum model, adding a damper and a couple of little terms in there related to inertia. This ends up explaining a wide variety of scale invariants. So this was work that was done by Monica Daly in collaboration with Jonathan while he was at Oregon State, showing that over several orders of magnitude, so a 200-gram small bird on the left-hand side all the way up to an ostrich, 2 to 3 orders of magnitude larger, that the same controls model can explain the behavior during a stance of the robot while it's walking on a force plate. This matters from a robotic design standpoint because it means that once we understand this math and once we have a control method that is able to control these sorts of machines, you end up in a situation where you can produce robots across a variety of scales. And because of a variety of interesting physics problems, you typically end up with different actuators at these different scales. So what you can get away with at a very small scale is different than what you need at a very large scale. So if you're designing an actuated robot that weighs 100 grams and is running around, it's the size of a mouse, material properties are actually strongly in your favor. So if you look at the heights that small animals can fall from without hurting themselves, for instance, it's because you end up with linear scaling on some dimensions and cube scaling on others. So from our standpoint, this is exciting. It means if we can solve the mobility challenge at one scale, we can go all the way up to heavy lift capacity robots for industrial applications or down to relatively low power, low cost applications, all with the same block of control theory, as opposed to having to tailor that to something that's particular to each robot. So lots of people over the years have tried to capture spring mass motion in a machine. So this was work that Ben Brown and Garth Zeglin did at Carnegie Mellon in the 90s. The work that Ben Brown and Garth Zeglin did was the CMU bow leg hopper. Videos of that are available on YouTube. So this was the initial origins of the Cassie robot. This was Thumper and Mabel. You may be familiar with the Mabel robot from University of Michigan. Thumper was essentially one half of a Mabel. So there was an NSF project that built 3 legs. 2 of them were combined together to form Mabel, and then one of them was Thumper. That evolved into ATRIAS 1.0, and this was work that was done at Oregon State University. That was up to ATRIAS 2.1 by 2013. There were 3 copies of this, one at Oregon State, one at University of Michigan, and one at Carnegie Mellon. So that was Jesse Grizzle at University of Michigan and Hartmut Geyer at CMU. Now, so this gets into the topic that I alluded to, which is, are we intentionally trying to make machines that look like the animals? In this case, no. So the starting point here is, of course, animal experiments, because that's our best reference for bipedal locomotion. That goes into a math model, which turns into an engineering project, in this case, the ATRIAS project, and then is turned then further into a commercial product, which is Cassie. So this enables a couple of things. If you compare these two videos side by side, the bird on the left-hand side has no idea that it's running down a runway and is about to hit a piece of tissue paper. So it was trained to run down a runway while being chased by a grad student. And what it's doing here is punching through the tissue paper. And if you actually look at the neural response time in biology, there is no active control that's fast enough to catch that leg behavior. So what's going on here is primarily a physics problem that's kind of baked into the hardware of the robot on the right-hand side, or the bird on the left-hand side. And ATRIAS exhibited very similar behavior. So the version of ATRIAS here had no sensing on it at all. So it was unaware that it was walking, in this case, outside or on those steps, and was able to sort of stumble and recover based on the physics of the gait, as opposed to 3D scanning the environment, having a plan of where it was going to place its feet, and so on. And so that suggests that, qualitatively, because we can see similar behavior here between the bird and the robot, that maybe we're heading in the right track in terms of what portion of this is software defined and which portion of this is mechanical defined. The problem here, though, if you think about this from a product standpoint, which is, of course, what we're interested in as a company, ATRIAS was pretty far from our product. So it had no ability to get up after a fall and would frequently tear itself to pieces when it fell sideways. So it had, the actuators that came out the side, very heavy upper torso, took a lot of engineering work just to keep the machine alive, much less have it be a useful product. So in 2014, this is sort of where I first got involved in the early stages of what became Agility. The university proposed a design concept for DARPA that they were calling at the time Silent Runner, and this is what evolved into Cassie in about a year and a half after the beginning of this project. So we got involved as a company formally in 2015. I spent the first year of the existence of the company working out the license agreement with the university. We took an interesting approach with our seed investment, which was to negotiate a lot of it in 2015. But because it would have just spent money on legal fees and not building robots, we chose to defer all of that until November of 2016. So we moved at a pretty quick tempo after that point. The first robot sale was to the University of Michigan in 2016, started shipping them the following summer. And then closed our Series A here just a couple months ago with Playground Global as the lead. We currently have a total of 14 employees. We have another 3 of them starting in the next 5 weeks. 12 of those are at the main office in Oregon, and then we're also opening an office in Pittsburgh in about a week and a half. We just signed a lease on that. Sort of conceptually, the split is that business development and software is in the Pittsburgh office, and electronics and mechanical stuff and robot construction is in the Oregon office. I'm not going to talk a whole lot about sort of our pitch, because that's not the point of this talk, other than to observe that platforms are products in and of themselves. So we are not, for instance, getting into package delivery by ourselves. We're saying that you can have a mobility platform that, when you add features and add infrastructure to it, becomes a delivery service. Or in the case of an automobile platform, you can take the same underlying technological platform and also have it be vehicle transport. So a lot of people would look at these and consider this 2 independent markets. We say, well, from our standpoint, what we're choosing to focus on is the mobility problem, which is common to these 2 different end-use scenarios. A way to think about that with robotics applications is to compare iRobot and Starship. And you can sort of imagine a case where if you were delivering groceries to someone who didn't have a driveway, we go to the Outer Banks every year, and there's areas where you can rent houses that are only accessible by 4-wheel drive across sand. We don't have 4-wheel drive, so we don't do that. But you imagine that there might be a business model down there delivering groceries with a tracked vehicle so that you could access it across sand, or conversely doing IED disposal in a strictly urban environment where wheels, for some reason, are a superior platform. So we're trying to emphasize the separability of the application-specific design choices that are made and the mobility platform itself. So we launched the robot in February of 2017. We allowed ourselves to be scooped by the university. We had intended to stay quiet about the existence of the company until that summer, but they were trying to do a president's address feature showing collaboration and launch of startup companies. As you imagine, there's not a huge number of robotics startups in rural Oregon. And so they decided to use us. Now, the nice thing with that is they have an extremely professional PR department and produced this video. So this was the university Cassie robot. This was, for counting purposes, we call this Cassie V1. I suspect the sound's on the computer side, but I'm not going to push my luck with PowerPoint misbehaving. And the design choices here, there was a little chin on the front of it that's not present on the commercial versions of Cassie. That was to hold a laser gyro that ended up not being necessary, that ended up being overkill for our application. And so Cassie V1 was assembled at the university, but all following Cassies that exist have been assembled at the company. All of the manufacturing is done in-house in Oregon. We do have a network of machinists that are local that we use. We had been stuffing the circuit boards ourselves. I encourage any startups to not stuff the circuit board yourself, just hire a contract manufacturer to do that. And then other things that we get outsourced. And another thing I would encourage is if you're needing to build specialty batteries, and we had a very particular need for being able to pull current out of and put current back into the battery on very short timescales. That was initially designed by us, and then we started working with a contract battery house to optimize the design. But other than that, all of the assembly and testing is done in-house. Obviously, as we would scale, we would push this off to contract manufacturers first for sub-assemblies and later for finished robots. But at least for right now, it's been a huge benefit because it allows us to iterate pretty quickly. We also adopted sort of a hiring practice where all the engineers that we bring in first have to work with our technicians to learn how the robots are built and sort of eat their own dog food. Because when an engineer designs something, they can, in some sense, wash their hands of the assembly process. And by forcing them to go through the support side of things and the construction side of things, it adds a lot, I think, to our workflow in terms of maturing the design. So these were the first three robots. That was University of Michigan, Caltech, and Harvard. I can say their names now because they've all tweeted about it. We have another 3 robots actually that were just delivered. The first one of that batch was delivered last week, and the next 2 are coming up here. They have not announced it publicly yet, but so there'll be a total of 6 customer robots that have been delivered with the next production run starting shortly here. So those were the launch customer builds. So that was Cassie version 2 on the far left, which was sort of the intermediate version transitioning away from the straight research platform, and then 3 of the first production runs of Cassies. So here's 2 of them wandering around our office. People ask, is the robot right now autonomous? And I'll get back to what that means, because it's actually a more complicated question than you might guess. Right now they're teleoperated, but they are teleoperated with intent rather than with marionette puppeteering kind of things. So in that sense, what I mean is, although you'll see in some of the videos, some of the remote control units standing behind the robot, they are sending abstract commands to it: walk forwards, turn left, turn right, squat down, stand up, not sending commands that are directly applied by the robot to the motors. So differentiating, say, between a radio controlled car where you're directly controlling the current that's going to the motors on the wheels versus you can imagine that the link here is simply projecting a little command to the robot or whispering in its ear saying it's time to walk forwards. And that is a lot more amenable to the AI stuff that I'll talk about in a second. So the Michigan acceptance testing and delivery was last August. That was the first time that we had one of these out in a group that wasn't us. And Michigan, if you follow their YouTube channel, has been quite enthusiastic with trying interesting ideas with their robot. Including this, which really surprised us. What's interesting about this is that nothing about our design was designed to allow the robot to ride a Segway. It's simply that the robot can balance and it understands how to lean forward and lean back and maintain its center of gravity. So in this case, because riding a Segway is just about standing and then shifting your weight, center of pressure on your feet forwards and backwards, they were able to get it to ride a Segway with very little modification. More interestingly, I can imagine myself doing that because I've ridden a Segway once. This I'd be personally a little bit more skeptical about. But again, at fundamental purposes is simply a balancing operation where by keeping yourself posturally upright, you can solve the balancing problem in a way that is very similar to how a human does it. So the most recent news from sort of a business development standpoint was that we wrapped up all of our Series A in March 2018. This is public information, so I'm not saying anything that's super secret here. The investors were Playground Global, which was Andy Rubin's fund that he started after leaving Google, Sony North America, and one of our seed investors, Robotics Hub from Pittsburgh. While we were at Playground, Cassie got to meet Spot. This is, I think, an interesting side-by-side comparison between quadrupeds and bipeds. But they had fun together. All right, so revisiting this result. So we got here with ATRIAS in 2015. One of the interesting side effects of the ATRIAS leg design was it removed a lot of the mathematical complexity. So with the 4-bar linkage, it canceled out this elbow and this elbow. So it allowed you to actuate directly along the axis of the leg, which is a lot closer to the slip model of actuation. And that ended up being a lot harder with Cassie, I think, than we expected that it would be. Cassie has a knee, so when you pull in one direction, there are components of the resulting vector at the toe that end up going in a direction that's not along the leg length direction. And I don't want to say we stumbled on that for a while, but for about the last year, that was a source of a lot of added complexity. So Mikhail, our lead controls engineer, started a project about a year ago taking apart the original controller design and rebuilding it from scratch. And I'm pleased to be able to show you today, we have not posted these videos yet, that it has paid off. So this is Cassie walking at speed, blind over steps. So again, we're not to the point yet of being able to graft a whole lot of world perception on top of this, and I'll explain why that's necessary on the next slide. But this does show that by not having to stop and think deeply about where you're placing your feet, you can maintain the motion. Also, because the robot simply perceives this as kind of a postural problem rather than a controls problem per se, you can see once we get to the next part of the video, that it's able to treat this as a sidestepping behavior in addition to a forwards-backwards behavior. So the same control algorithm that works walking forwards also works from a sidestepping standpoint. And we think this is the first time that a biped has walked at speed over steps. It's a claim that I would want to research before I firmly stick a stake in the ground. But so that's an interesting result, and that was actually just from last week. All right, so what about autonomy? That's great if you're indoors in a relatively controlled environment. Where this breaks down, interestingly, and there's some work with gait research from humans, is that we plan about 2 or 3 steps ahead, not much farther than that, and that the behavior in a lot of applications is actually dominated by the clockwork physics behavior of your legs up to a point. So in other words, if I'm trying to climb steps, I can approach the staircase, set my gait frequency, and then proceed up the steps without thinking about it a huge amount. Where that goes wrong is something that I'm sure everybody here has experienced, which is you're going down a flight of steps, usually carrying something so that you can't see the bottom, and you step down, there's the last extra step where you break your kneecap. And that's illustrating the disconnect between sort of a clockwork physics-based approach and a more robust approach that includes some planning knowledge. So just to illustrate that with Cassie, and this is using our simulator, sort of things go well and then not so great. And so this is why you need planning. So, to the extent that up to this point we are a predominantly physics company, we are now transitioning into trying to seed the behavior of the machines a bit more intelligently with some autonomous behavior. And the way that we're approaching that is sort of shown on the right-hand side here. We're trying to treat the planning process as a choose your own adventure, as opposed to an inverse kinematics problem. So the robot knows how to do a bunch of things, knows how to step forwards, it knows how to change its gait height, gait frequency, turn left, turn right. And the planning problem becomes planning through the kinematic space of those options as opposed to inverse kinematicing back exact foot placements. So on the bottom right, we view the world as a series of stepping stones. Doesn't matter where on the stepping stone you land, as long as you can plan a physically plausible route through it, you don't have to obsess too much about the actual ground contact. So that's been implemented first in a simplified planning model showing that by adding and removing energy from the gate, you can stutter step to set your gate and then hop down off of a ledge. And then the same behavior can extend to steps where you set your stride frequency to a point that allows you to go up the staircase, and then you can kind of go from there for free after the gate is set. For people who are interested in some of the technical background, this is actually a Monte Carlo search. So again, because we have this stable of behaviors we can pull from, the space that we're trying to plan through is significantly more constrained than all of physics. Because if we had to include the option to leap up into the sky like Superman, or maybe we crouch down and walk like a duck, that's a hard problem to plan through. But the available options that the robot ends up considering is actually relatively small. So you'll see here, it tries a bunch of options, falls on some of them, and keeps walking on others. And it just picks the one that allows it to keep going the longest, and then the planner updates the next step. So this is obviously kind of a toy approach here. Again, this is a very simplified controls model, but because the robot is designed to encapsulate this physics, it does extend pretty well. So the next part of this video shows the planner running in full 3D using the same model that we actually use for controls development. So although this looks a lot like some of the physical videos that we have that have been radio controlled, this is actually operating fully autonomously. So it's using the real control system on the robot, and the only thing that's simulated here that is not physically implemented on the robot is knowledge of the world space. But you can imagine this sort of problem being a relatively simple machine vision problem. You could solve it either with LiDAR or with real-time stereo. And the actual planner, in this case, is being forced to run hard real-time along with the control system. OK, so what about deep learning? I'm sure most of you are familiar with this video. This was from Google DeepMind's grafting deep learning onto a biped. And earlier in the video, there's a bunch of pretty humorous clips that I did not include because I'm not trying to make fun of their results. And this was showing that with a physics system, there are learning approaches that result in something that's a bit like what you would expect from a bipedal system. And we're taking very early steps with that. And this is work that was done at Oregon State and then also a collaboration with UBC. This is also a video that was actually just released yesterday at Dynamic Walking in Florida. So the idea here is to say, like, look, we have this physics-based approach for Cassie. What do we do as the next step? How do we graft higher level learned behaviors on top of that? So the reference motion on the left there was derived from the physics controller. This controller that's shown here is actually entirely learned behavior. So can we get to a point where there is a higher level AI mind on the robot that understands enough of the physics to allow it to move? Now, the real world, and I'll talk about this on the next slide, is probably a combination of the two, and there's good evidence that people behave this way. So a lot of your behavior at the quote-unquote unconscious level is either strictly physics-based, based on the geometry and physics of your legs, or extremely low-level neural stuff, so spinal cord and down in terms of the reaction. And so there's not an either-or situation. You might need both deep learning and the physics-based controllers, which leads to this. So we like to think of there being 3 levels of controls and then the 4th level being physics in terms of things that define the behavior of the machine. So if you think of layer 0 being the physical hardware, layer 1 is the really fast control loops. So from a controls engineer perspective, these are the things that are going at 2 kilohertz, super fast, tight control loops. At layer 2 is learned motor strategies. So that's, I know that I need to adjust my gate frequency slightly on steps or I'm going to fall down. And then high level planning is I need to go up the steps. So understanding intent and mission goals. How you might map this onto automobiles, and the analogy is imperfect, but it's useful to think about, are that the physics of the car occurs at the design level. So that's how does the engine work? How do your cylinders all get fuel? Fuel injection is, all right, I know how to feed fuel to the engine. How much do I give it? So that's a really tight control loop that monitors the oxygen sensor in your tailpipe. Layer 2 is the car is in a slide. How do I chatter the brake system so that the car straightens back out for anti-lock brakes? And then layer 3 is self-driving. And what's interesting with this is that the self-driving revolution arguably requires all of the above layers to exist. So if you had an old school Model T, making that a self-driving car would be a hard problem because you can't just abstract the AI away from the control system. And we're trying to think of this as sort of a similar issue then, where right now we're selling to controls theorists who are mostly interested in this layer 0, having a robot that's mechanically able to walk. by the time we're up to the next product launch that we're looking ahead to next year, we hope to be able to sell people who are starting to take applications engineering goals in mind, so AI developers. In other words, ignoring all the things that are required to sort of posturally keep the robot upright, and they're worried about control from the standpoint that starts to look a little bit more like using this as a mobility platform and less as a cool bipedal robot. And we expect that most customers actually want to use the robot here, not at those lower levels, where you can simply imagine yelling things at the robot that you're riding on. Go forwards, and it knows enough to not fall over the curb, it knows enough not to walk into traffic, and so on. A lot like the analogy of this very dapper gentleman from the 20s riding his trusty steed. So in other words, we would like to be the ostrich, and we'd like to give you the pleasure of riding. Not literally, we're not offering Cassie rides yet. And so, to show you a video of sort of where we're at, this also has not been released. So this is showing sort of what we can do outside now, crossing different terrains. This was about a 5.5-minute continuous walk, obviously edited down quite a bit. So all of the behavior here with the ground contact, showing the transitions across surfaces that have different stiffnesses, is all behavior that's simply baked into the robot. And this is heading in the direction of having the robot simply be an abstract platform that can be available to customers as opposed to requiring you to be a legged robotics expert. So let's let this run for a second. There's a particular spot in this clip where it steps on a root growing across the path. Again, we're not 3D scanning the environment and planning for those sorts of disruptions. That's simply baked into the control system. So that'll be online. I'll let you watch the whole thing at your convenience. Some hard problems with this. So e-stop with a legged platform is an interestingly undefined problem. What I mean by that is that with a car, if you imagine you're doing self-driving, e-stop is frequently max brake effort, let the anti-lock brakes and the vehicle stability control keep you going in a straight line, stop you as quickly as possible. It's not clear what slamming on the brakes means for this guy. Certainly, you don't want to turn his power off. That's a problem both for the robot and for anybody who happens to be in front of it. And that's something we're looking at right now. Our best guess at this point, and I'd be interested if anybody has an interesting idea on this, is that e-stop for a legged platform means to reduce the joint torque limit significantly, such that you're basically coming to a stop. And you look at this with people who are really good at taking falls, so mixed martial arts, karate people, that kind of thing, where you're sort of accepting the fall and then damping out the consequences as opposed to simply passing out and collapsing to the floor like I would do. And so we want to be careful here that there's two goals for the e-stop. First and most important is don't hurt the environment or people in it. And second is don't destroy the robot. And the e-stop process for legs is something that we're going to be actively working on for a while yet. And then the second problem is failing gracefully. I'll pick on Jesse just because he loves to post these sorts of videos. This was actually footage the Associated Press took. It's been good advertising for us because our primary design goal for Cassie was don't break when this happens. And fortunately, we've been quite good at this. So the question is, how do you recover from that? What would a person look like? Well, sometimes people don't recover from that, which is why emergency rooms do a good business in broken arms. But from a robustness factor on the robot, after this happens, we need to be able to get back up, survive the fall without damage. And as I said with the e-stop question, more importantly, don't hurt people in the environment or the robot in that order. So we're pleased to announce today that we're releasing actually our sims available for public use under a BSD license. The first of the two that we're releasing is actually available now. It's available from GitHub, and that's Mojoku. And then the one that people are more familiar with is probably Gazebo. That's still under development. We're finishing that up. We'll be releasing it in July. So if you have controls ideas that you try, keeping in mind that at this point this is intended for people who want to control the robot at a lower level, that those sims are really for that audience as opposed to people who are trying to graft higher level stuff onto it. But the video from UBC in Oregon State was done with the Mojoku sim. So it's the same tool set that we use internally to develop for the robot. And one of those two tools is available now, with the next one coming out in July. We're also starting the next production run here shortly. We're taking a month to reset, do inventory, and do some remodeling out in Oregon, but shortly thereafter we're getting back into building robots. And then we're hiring both in Oregon and Pittsburgh. We're into the phase of growth of the company where I haven't met everybody that works for me, which is an interesting experience. But we're glad to be hiring, having a lot of fun with the company. So hopefully that leaves a little bit of time for questions. We did have a great eclipse out in Oregon last year. Cassie enjoyed it. Fortunately, she didn't have eyes, so there wasn't any risk of her burning out her optical sensors. But thank you.
We still have time for one or two questions. Does anybody have a question?
Yeah, so the question was load carrying. Yes, we have. The numbers that we have are going to sound a little bit physically implausible, but that's because our hips are vastly more powerful than they need to be. So we can walk steady state with about a 20 kilogram load, so about 40 pounds. So imagine putting a sack of concrete on the robot. Cassie can squat its own body weight continuously, which is about 70 pounds. That's standing and then just squatting up and down at about a half a hertz rate continuously. And then it's held under a static load application up to 100 kilograms, which was Mikhail climbing on top of the robot to see if it would balance. And it did without killing him, which is a bonus for our insurance policy. So yeah, that's a really interesting one. So we have a 1 kilowatt battery pack, 1 kilowatt hour battery pack, which gets us about 8 hours of runtime mixed usage. Right now, the computational load on the robot, because we did not optimize for that, is about 50% of the total load. Walking steady state takes around 200 watts. So in very rough numbers, if we were to just walk in a straight line until the robot was exhausted, it would be about 3.5 hours of continuous runtime.
We're going to take
Thanks.